If you have troubles thinking of qubit states as vectors, or if you're in general more a visual thinker, then the Bloch sphere is probably a great tool for helping you understand the basics of quantum computing. We can represent quantum states, quantum gates, and quantum measurements using the Bloch sphere tool. So hopefully after this video, these concepts will feel much more intuitive to you. The north and the south pole of the sphere correspond to the 0 and the 1 state. And on the x-axis are the x eigenstates, plus and minus. And on the y-axis are the eigenstates of y. The qubit is then represented as a vector from the origin to an arbitrary point on the sphere. The reason why we can use the Bloch sphere for visualizing a qubit has everything to do with the Born rule. The idea is that you can write any pure qubit state as a superposition of the 0 and the 1 state. So psi is alpha 0 plus beta 1, where the coefficients alpha and beta define the probability that the state is in the 0 or in the 1 state. The coefficients satisfy the rule that the absolute value of alpha plus the absolute value of beta should be 1, because of the total probability rule. So we can see that every pure state vector psi has exactly length 1. And this is the reason why we can represent any qubit on a unity sphere, aka the Bloch sphere. One reason why the Bloch sphere is such a useful tool is because it's easy to visualize gate operations on a qubit. Gates are represented as rotations on the Bloch sphere. Let's look at an example. Suppose we have the qubit state 0 and we want to perform an X gate. The X gate is also called the bit flip gate. It brings the 0 state to the 1 state, and on the Bloch sphere, the X gate is equivalent to a rotation of pi around the x-axis. The other Pauli gates work in a similar way, so the Y gate is a pi rotation around the y-axis and the Z gate is a pi rotation around the z-axis. Another gate that is often used in quantum information is the Hadamard gate. On the Bloch sphere, the Hadamard gate is a pi rotation around an axis right in between the x and the z-axis. It brings the 0 state to the maximal superposition state plus, and it brings the 1 state to the minus state. The Hadamard is equivalent to a pi over 2 rotation over the y-axis and a pi rotation around the z-axis. If we do a measurement on a qubit in a certain basis, its wave function will collapse to one of the basis states, with a probability given by the Born rule. We can make this more intuitive by looking at an example on the Bloch sphere. So if we have the state psi is 1 over square root 3 ket 0 plus square root 2/3 1, and if we measure in the z basis, we will observe the state either completely in the 0 state with probability 1/3 or completely in the 1 state with probability 2/3. We can see that the measurement in a certain basis projects the qubit state onto one of its eigenstates. And that's why the direct measurement of a qubit is also called a projective measurement.